if you have any kind of system with stuff going on, if no net force acts on this system, the total momentum inside the system will stay the same, which means that the momentum inside is a conserved amount. It doesn't decrease, it doesn't increase. What does that mean? Let's take an example. Imagine two ice skaters. So this is ice skater 1. We'll label him A. And this is ice skater 2. We'll label him B. And they're wearing ice skating shoes because they're ice skating. Let's say they're very clumsy and they bump into each other and they collide. Their individual momentum will change. They'll slow down and go in a different direction after bumping into each other. However, in total, the sum of their momentums, the P of A plus P of B, stays the same after this collision. And so let's set up some math that we'll use in this video. The total momentum before the collision is the vector sum of both of their momentum. So that would be mass of A times velocity of A plus the mass of B times the velocity of B, because that's the momentum formula, right? And that's the total momentum in this system before the collision. After this collision, this horrible tragedy, they now have a changed velocity and direction. So their momentum is different. The momentum of guy A after the collision, we will denote with this symbol. This is called priming the quantity. So it's denoted with a prime. And this is simple. And really, it's just a label. It means this, but after the collision. And we'll do the same thing for the second dude. His momentum after the collision. Following the collision, the total momentum in the system is the same as it was prior to the collision, because there's no net force acting on them. It's just these two guys. And this right here is the equation for the conservation of momentum. Before we solve problems, let me explain another concept for you. Newton's third law guarantees that inside an isolated system, what's an isolated system? Well, it's the set of objects that we choose. For example, the two ice skaters. Inside an isolated system, internal forces will cancel. What does that mean? All you have to worry about is that inside an isolated system, momentum will be constant, like we just discussed. But only when there's no external forces. But what if there is an external force? Then momentum wouldn't be conserved anymore, right? It would change unless you redefine your system. Let me explain this to you. Imagine you throw a ball into the air, and then the ball on the way up will slowly slow down because of gravity, and then it'll speed up. The momentum of this ball specifically is changing. It's low up here, and then it's higher on the way down. The total momentum in this system is not constant because there's the external force of Earth's gravity. But if you redefine your system as the ball plus Earth, then the total momentum is conserved, because as the ball goes up, Earth actually goes down by the tiniest amount, which means that in total the momentum balances, it stays constant. But only because we included Earth in our system. Now here's a note, the conservation of momentum is more fundamental than Newton's laws. Even when Newton's laws fails at the atomic level, conservation laws of energy still hold, especially for momentum. So it's more universal. Here's a proper example now. You have two people playing hockey. This is person A, and this is person B. And person B is shocked because person A is flying toward person B at 7 meters per second. Person A is 90 kilos and person B is 70 kilos. After this collision, they grab onto each other and slide off together. What's the final speed after this collision? Okay, let's set up our problem. Because of the conservation of momentum, we know that the total momentum before is equal to the total momentum after. The total momentum in this system before is the momentum of dude number A, which is the mass of A times the velocity of A, 90 kilos times 7 meters per second. And it's equal to the momentum in the system after. The total momentum in this system prior to the collision is the momentum of dude number A plus the momentum of dude number B. Momentum of dude A is 90 kilos multiplied by 7 meters per second. And dude number B, he has a mass of 70 kilos, but he's at rest, so his momentum is 0. We just won't write that. But because they stick together after colliding, grab onto each other, and slide off together into the sunset, then we will consider their mass as 1. So mass A plus mass B multiplied by their velocity. And this velocity will denote with a prime to state the velocity after, because we don't want to get it mixed up with this velocity initially. Let's do the math. This is 630, and it's equal to their total combined mass, which is 160, multiplied by their final velocity. Divide both sides by 160 so that we can isolate the final velocity, by the way, is what we're looking for. Then we get final velocity is somewhere around 3.7 meters per second. So after they collide and stick together, slide off, this is how fast they're going. And we had to use the conservation of momentum instead of things like the kinematic equations, because there's two objects and they stick together after. So it's a little bit more complicated, and the conservation of momentum gives us the answer perfectly. Here's the second problem. You have a cannon. Here's our cannon. It's got a wheel, fuse. Anyway, the cannon is 2,000 kilos. And the cannonball that it fires is 20 kilos. It's initially fired horizontally at 250 meters per second. The cannon itself is initially at rest, and if we don't consider friction, what is the recoil speed after it fires this cannonball? Let's break this problem down. So first, let's identify what we're given. We have the mass of the cannon, 2,000 kilos. We also have the mass of the cannonball, which we'll label with B for ball, 20 kilos. We have the velocity of the ball initially, 250 meters per second. And we also have the total momentum initially, which is 0. Why is it 0? The ball hasn't been fired yet, so 0. And here we have to use the conservation of momentum because there's things moving back and forth and things are being balanced by each other, like the recoil, which is based on how hard the cannonball is being fired. Because momentum is always conserved inside an isolated system with no net forces, then we have to use the conservation of momentum to find the correct answer. Let's solve. So we know that the total momentum inside this system is the momentum of the cannon plus the momentum of the ball. And initially, it's equal to 0. The total momentum in the system before firing the ball is the momentum of the cannon plus the momentum of the ball. And initially, it's 0. Now, what are we looking for? We're looking for the cannon's recoil velocity, right? And that's this value right here. So let's move this to its own side. Mass of the ball plus mass of the velocity. Momentum of the ball is equal to the negative momentum of the cannon. Now we will divide by mass of the cannon to fully isolate the velocity of the cannon. And you get this equation right here. So now we've set up an equation where we can solve for this. And we got this from the momentum of conservation equation. By the way, there's a lot of formulas like this going on here. And there's a free cheat sheet I made for myself in the description if you want it. Plug in our values because we know everything here, right? Then you get the answer as negative 2.5 meters per second for the recoil speed after firing the cannonball. This is a small amount, but remember that the cannon is 2,000 kilos. And it has recoil speed because momentum needs to stay balanced. It can't just fire the ball and stay completely still. By the way, something that really helps me is having all the formulas you ever need in one place. And I make these cheat sheets for myself, and if you want your own, it's in the description for free. So go sign up. It helps you while you solve problems.